So this is the first lesson in the hyperbolic functions pack. Hyperbolic functions are very, very similar to trigonometric functions. We're going to define them in terms of exponential functions, and actually you can also do the same thing for trig functions, which we'll see later on in the complex numbers 2 pack. We've got hyperbolic versions of all of the usual trig functions, so sine, cosine, and tan we're going to focus on, but you can also have them for sec, cosec, and cot as well. The verse of hyperbolic sine we write as sine h. You would pronounce it as shine, and it's defined to be shine x is equal to e to the x minus e to the minus x all over 2. So you need to learn that definition for shine x. Similarly for hyperbolic cos, we call it cosh. That will make sense. So cosh x is a very similar thing, except instead of a minus on the top, it's a plus. And then from these two, you can derive hyperbolic tan. Some people pronounce it as than, or some people pronounce it as tanch. I will say than. It's defined to be obviously shine over cosh, which you can simplify down to e to the x minus e to the minus x over e to the x plus e to the minus x. You may see this written in terms of e to the 2x as well. If you challenge the top and bottom to write e to the x, you can get that too. But you need to learn these definitions for hyperbolic functions. Like I mentioned earlier, you can also have your reciprocal ones. So you have cosec, sec, and cot as well. It's useful to know what the graphs of these things look like, so you can draw them on your calculator. So your calculator has the hyperbolic function in it. If you press option, and then you'll see this hyperbole in F3, it's there. You can put all of those in. So if you wanted to draw the graph of shine x, we'll look something like this. Kind of looks like a y equals x cubed graph. It doesn't have asymptotes. It looks like a tan wiggle, but it doesn't have asymptotes. It does carry on going up forever and down forever, and goes through the origin there. So draw that in your pack, something looking like that. Crosses through the origin 0, 0. It does have rotational symmetry order 2 around the origin. Although it looks like it might have asymptotes, it doesn't. And so its range is just all y values. But notice it's a one-to-one function, so when you're solving this, you will just get one solution, equations of origin. Similarly, you can draw a cosh. Option hyperbolic cosh x. Looks like this. So it looks like a parabola, looks like a y equals x squared. It's not quite a parabola, it's something called a catenary, which you can look up if you like. This how a rope hangs is forms in a catenary. Notice this one goes through the y-axis at 1, has a minimum point at 1. So there are some values where you won't get solutions. And it's a many-to-one function, so you will get 2 solutions most of the time when you're solving with cosh. So the graph of cosh looks like this. Crosses the y-axis at y equals 1. It's got a line of symmetry down the y-axis. Again, no asymptotes. So the range is y is greater than or equal to 1 for this. Finally, we can draw tan in our calculator, so I'll call it tan x. So it looks like this. Looks like an inverse tan sort of graph. So this one does actually have asymptotes at 1 and minus 1. It does have rotational symmetry around the origin, goes through the origin. And so its range is in between 1 and minus 1. Your calculator will do calculations involving hyperbolics. So these firstly, it's really easy just substituting into the calculator. So again, option, if you press F6 to scroll along there, you'll find hyperbolic, and then you can work out, for example, shine as 3. That will be 2. You can work out cosh of 1 at 1.54. And you can work out tan of 8. That's it, not. Very much one for that. Example 2, find the exact value of tan ln4. So you could type tan ln4 into the calculator, and I think it probably will give you the answer. No, well, 15 over 17. Or we're going to do this one by hand. So if I start off with my definition for tan, which is sine over cos, so it's e to the x minus, or e to the ln4, so minus e to the ln4 and minus ln4 over cos, so ln e to the ln4 plus e to the minus ln. So that's my definition for tan. Right. E to the ln4, you know, is just 4. E to the minus ln4, well, you set the minus up to make that 4 to the minus 1. So it's e to the ln of a quarter. And the e and the ln cancel out, and it's going to be a quarter. So you get 4 minus quarter over 4 plus a quarter. You could just type this into your calculator. That's what on the top is 15 over 16, on the bottom it's 17 over 16. So you get the 15 over 17, which your calculator did give you, but you do need to go through that by hand. Now, sometimes when we're solving hyperbolic equations, you'll want to use the exponential definitions. So this one asks us, here's the definition for cos x. Find 2 decimal places the value vectors of x, which cos x equals 5. Notice it says values because cos x, remember, was a many to one function. So you will have multiple solutions for that. So I've written the definition in, so cos x is e to the x plus e to the minus x over 2. I'm going to times it by 2. And then what I recognize is this is going to be disguised quadratic in e to the x. So if I times everything through by e to the x, okay, e to the 2x, e to the x times e to the minus x gives me 1, 10. So this is disguised quadratic here in terms of the x. I'm going to solve this quadratic in my calculator. I've got e to the x squared, or minus 10 e to the x. And I've got 1 there. Gives me 2 solutions. So I get e to the x equals 5 plus 2 root 6 and 5 minus 2 root 6. 5. 6. So let's get x. And ln that, and I get ln 5 plus or minus 2 root 6. You can check that both of those are positive. So you can ln them, no problem. Have we got the U try? Pause the video and I'll reveal the answer in a second. So because we're solving here for sin x, we will just get one solution. Remember, the graph of sin x is a one-to-one function. Using the definition, turning it into a disguised quadratic, you can solve and get 3 plus root 10 and 3 minus root 10. But 3 minus root 10 is negative, so you get no solutions for this one. The only solution you get is ln 3 plus root 10. Just to realise, this one did say decimal places, so let's work these out as decimals. 6. 0.29, or if I change it to minus 2.29. So notice these are linked to each other, which makes sense because cos x has a line of symmetry down the y-axis. We're going to have to solve this one using the definitions as well. So I'm going to put in the 6th definition of sin x is e to the x minus e to the minus x over 2 minus 2 cos x plus e to the minus x over 2. So I'm going to expand this out, so 6 over 2 obviously is 3, so you get 3 e to the x minus 3 e to the x. 2 over 2 obviously is just 1 times by minus e to the x. Minus x and that equals there. Collecting these up, so 3 e to the x minus e to the x is 2 e to the x minus 3 minus 4. 7. And I'm going to do what we did before, time it through by ECX to turn it into a disguised quadratic. Bring that 7 ECX across and make it equal to 0. So we've got a disguised quadratic here in ECX. We're going to solve this on our calculator. 7 minus 4. My solution, so this is e to the x is 4 This one has no solutions because you got a negative. So the other solution to this one is x equals ln. Please pause the video and have a go at you trying, and I'll reveal the answers. We're doing the same thing on here, using your definitions, turn it into a disguised quadratic into x. You get two solutions which are both valid this time, so you get x is ln 7 and x is ln